Hey, everybody. In this lesson, we're going to learn how to use the conservation of momentum and the conservation of mechanical energy in order to solve physics problems. So, I'll say that this is a very common type of problem to be given on the AP test, and for a good reason. It forces the students to show that they understand which physics concepts apply to which situations. And so, because this combines two of the more important laws of physics, conservation of energy, conservation of momentum, these problems are really good at determining the degree to which students understand their physics. So let's just see how we're going to approach this. All right, so here's a classic problem. I have an object of mass m. It's released from height h1. It's going to slide down a frictionless surface, although there could be friction too. It's going to collide perfectly inelastically and stick together to mass m, and it's going to slide up the other side, and we want to know what is the final height h that will be reached by this. Pretty simple question to ask, and really not that hard to do. You just have to know when to apply which concepts in order to solve it. Okay. So here's my advice to you, and you need to follow this advice because it works. So, first of all, if you start off with an object changing from one height to another, you have to use conservation of energy to find its final velocity prior to the collision. If there's no change in height, then you don't have to, or no work being done by friction, you don't have to do that. But if there's a reason to think that its kinetic energy is changing prior to colliding with the other object, then you have to use conservation of energy to find out what is the velocity of the object immediately prior to collision. Now, once it collides, you have to use conservation of momentum. There's no way to find out what the velocity is afterwards other than using conservation of momentum because we don't know how much of its energy is going to be converted from mechanical energy to thermal energy or internal energy. So the trick is use conservation of momentum. It always works. Then afterwards, we know how fast the objects are moving. So then we know what their kinetic energy is. So we can therefore once again apply the concepts of conservation of mechanical energy and work to figure out basically how high the object will go afterwards, which is a common question to ask. So let's just start off with one that's fairly simple. And it's just, I'm going to let this object slide down, collide with this, and I just want to know what is the speed of the combined 2m object after they collide inelastically and stick together. Okay, we assume that friction is negligible, although, in class we'll do it with friction non-negligible. Okay, so remember, this object changed height. So the first thing I've got to do is I've got to use conservation of ME to figure out, well, what is its velocity immediately prior to collision? Because I can't do conservation of momentum unless I know what the velocity is. So here we go. I'm going to say, well, I'm going from, I have basically starting from rest, so it has no kinetic energy. So I'm simply going to use this form. MGH is going to equal 1/2 mv squared. I'm going to be converting all of the object's mechanical energy in the form of potential energy, gravitational potential energy, into kinetic energy. All right. So now I see that the m's cancel out. I can multiply this side by 2, and I end up getting the final velocity equals root 2 gh. We've done this a million times. Hopefully by now you could just jump right to this without having to work your way through it, but it's good exercise to work your way through it. Okay. Now what I want to know is how fast they're going after the collision. So now when there's a collision, you must use conservation of momentum. When there is a collision, you must do that. Okay. So conservation of momentum takes this form. In this case, because it's perfectly inelastic and the two objects are going to stick together, I'm going to use this form of it to simplify things. I could still say equals m1 v1 plus m2 v2. It's just that the v's are going to be the same afterwards. Okay. So let's see what that means. I start off with this object had mass m, and remember its velocity immediately prior to collision was root 2 gh. And this one had a velocity of 0, so I'm just going to take this expression and just call it 0. Afterwards, what I have is an object that has a mass of 2m traveling at some unknown velocity v. And I just want to solve for v. Well, I know everything but v, so it shouldn't be too hard to do. So I'm going to get rid of my m's, and I just see that root 2 gh equals 2v, so therefore v equals half of that. It wasn't so hard. The trick is to know at first there was a change in height, so I had to apply conservation of mechanical energy. Afterwards, there was a collision, so I had to use conservation of momentum. Okay. Well, let's go back to that one I showed you to begin with. Okay. So it's the same problem as before, except now what I want to know is what is the final height that the two blocks reach after they join together? All right. Well, let's give this a try. And again, we're going to assume no friction. So again, I'm starting off with a change in height, so that means there's a change in change in the form of the energy from potential to kinetic. So I'd use conservation of momentum to find the velocity of this object prior to collision. So we just did this before, so I'm not going to really talk my way through it. Okay, so now I know how fast this is going immediately before the collision, and they're going to collide. And as we said before, after they collide, we're going to use conservation of momentum. And again, we just did this, so we know that this is how fast they're going after they collide. Now I want to know how high up the ramp are they going to go. Well, now that is a change in height, so that means they're going to be converting their kinetic energy into potential energy. So I'm going to have to use conservation of energy once again. Anytime I have a change in height or I have friction, anytime there's a change in kinetic energy, I'm going to have to use that. So I'm going to say, well, I had kinetic energy. I end up with potential energy. And so I'm going to substitute in, this was the velocity that we determined they had after the collision. So I'm just going to substitute that in. I'm going to get rid of my m's because, as often is the case, it doesn't really matter. And then I just have to simplify this a little bit. And what I'll find is the height I end up is 1/4 the height that was here. Now, it's important to note, we haven't yet talked about center of mass. We are going to be talking about center of mass, I think, in our very next lesson, if I'm not mistaken. So for right now, just say, this height 1 should be measured from the center of this object's mass. And this height 2 is the center of these objects' mass. So I have this, because they have the same mass, their center of mass is in the middle. We're going to learn how to figure out what the center mass is when that's not the case. But just so you know, that's what you had to do here. All right, let's try another one here. Okay. I have a cart that's coming in. It is not changing height. It's just coming at one speed. It's colliding with this 2m object. It's bouncing off and going the opposite way. And I want to know, how high does this object swing? Again, very classic question to ask about this. Okay. So let's give this a try, shall we? Okay. So I'm going to have to start in this case with conservation of momentum. No conservation of energy, because there was no reason to think that the velocity of this object changed, right? So there's no change in kinetic energy. I don't have to use conservation of energy. If this was sliding down the hill, I'd have to. If there was friction, I would have to. But in this case, I don't have to worry about that. So I'm going to start with, well, when they collide, I have a collision that's going to take this form because they're not sticking together. So I'm going to say it's going to end with m1v1 going one way and mv2 going the other way. So let's just substitute our values. So I know I have m and v. I have 2m, but it's going velocity 0. Afterwards, I know I have mass m, and be careful, it's going to the left now, so that's negative 1/3. It is easy to forget that, and it screws everything up. So that's negative 1/3 v1, and I want to know what v2 is. All right, and I have to keep in mind it has a mass of 2m. So first thing I'm going to do is I'm going to get rid of all my, I didn't get rid of all my m's yet, I guess. Okay, I'm just going to tidy this up a little bit. So I'm going to move this over, so I get 4/3 mv1 equals 2 mv2. Now I'm going to get rid of my m's. And I'm going to divide both sides by 2, and now I know how fast it's moving. But I'm not done. All I know is that's how fast this block was going immediately after it collided with this one. Now I want to know how high it goes. That's a conservation of energy question. So in that case, I'm going to use conservation of energy to figure out how high it goes. Now, to do that, I'm saying, well, it started off after the collision. This block had some velocity, so it had kinetic energy, and it's going to convert that into mgh. It's going to stop at a certain height, and all of its energy is going to be converted into potential. So I'm going to say, well, what was its kinetic energy? It has a mass of 2m. So I'm going to say 1/2 mv squared. It had a mass of 2m, and we just determined that it had 2/3 v1 was its initial velocity, and that's going to equal 2mgh. So therefore, I'm just going to get rid of my m's. I'm going to go ahead and square this through here, and then I'm just going to go ahead and divide through. And what I'll see is the height is going to go is going to be defined as 2 times the initial v squared over 9g, which is not intuitive, but it's correct. Hey, thanks for watching. These are fun. We'll do this in class. I think you'll like them. All right, bye.